So in this video, we're going to take our first step toward establishing the linear algebra technique for solving systems of equations more efficiently. And before we can even get started on doing that, we need to understand how to take a system of equations and represent it using the main tools and objects of linear algebra, which are matrices and vectors. So that's what today's lesson is focusing on, taking a system of equations and representing that system using matrices and using vectors. So if we have, for example, this system of equations from the end of yesterday's video, there is a matrix that's associated with this system, which is called the coefficient matrix for the system. And as the name suggests, the coefficient matrix for this system of equations is constructed by reading off the coefficients of all the variables in all of the equations in the system. So, for example, in the first equation, the coefficient on x is 1, the coefficient on y is 2, and the coefficient on z is 1. So I'm going to build my matrix by putting those three coefficients in the first row for my first equation. 1, the coefficient of x, 2, the coefficient of y, 1, the coefficient of z. The next row in the coefficient matrix is made by the coefficients of the second equation. So in our case, 2 is on x, 1 is on y, and 1 is on z. The third row is from the coefficients in the third equation. So we have -1 on x, 3 on y, and 1 on z. So this 3 by 3 matrix is the coefficient matrix corresponding to this system of equations. It has 3 columns, 1 column for each variable x, y, and z, and it has 3 rows, 1 row for each equation in the system. Equation 1, equation 2, and equation 3. This is the coefficient matrix corresponding to a system. Now, when you are representing a system using matrices and vectors, there is also a vector that stores the variables that are being used in the problem. So I might call this vector x with an arrow on top of it, and the vector x in this case is going to be a column vector that is storing the 3 variables that are being used in this system. So the variable x, no arrow, the variable y, and the variable z. So this is the second component that we use when we represent systems of equations using matrices and vectors, a vector containing the variables in your problem. The final vector that we use when we are representing a system in linear algebra format is a column vector that represents these constants on the right-hand side of the system. So these constants 1, 2, and -1, we're going to take these values and we're going to stick them into a column vector which is traditionally denoted by the notation b with the vector arrow on top of it. The column vector 1, 2, -1, consisting of these values on the right side of the system. Now, if you define these 3 matrices in this fashion, coefficient matrix, variable vector, and output vector, consider what happens if we think about the matrix equation A times X equals B. Let's see what happens when we evaluate this matrix product on the left-hand side. So using the dot product process, if I do on the left-hand side first row times this vector, then I would have 1 times x, I would have 2 times y, I would have 1 times z all added together. That would be the first entry in the result of this matrix product on the left. If I do the second product, second row times the vector, then from that dot product calculation, I would have 2 times x plus 1 times y plus 1 times z on the left side. If I do this third row times this vector, then that dot product would give us negative x plus 3y plus 1 times z on the left. And so what we get is a vector equation where x plus 2y plus z must equal 1, 2x plus y plus z must equal 2, negative x plus 3y plus z must equal minus 1. So in other words, we've got an equation that expresses exactly the same set of restrictions as our original system. So all this to say that this system of equations is identical and equivalent and has exactly the same meaning as the matrix equation
AX equals B,
where A is the coefficient matrix, X is the variable matrix, and B is the matrix of the desired results. These guys are exactly the same. They're just expressed slightly differently. So any system of equations can be represented as an equation in terms of these matrices and these vectors. These are exactly the same. So some important pieces of terminology for us. Once again, when we talk about the coefficient matrix for a system of equations, then the coefficient matrix, as the name suggests, is the matrix formed by taking the coefficients out of the system. So that's one important piece of terminology that we will be using a lot as we talk through the next several lessons. Another piece of terminology that we will often be referring to in the next several lessons as we discuss this process is what's called the augmented matrix. Augmented matrix. The augmented matrix is the matrix formed by taking the coefficient matrix and attaching the vector b as an additional column on the right. So in the case of the previous example, the augmented matrix is typically denoted as A and then a vertical bar with B next to it. And in the case of this example that we've been working with up to this point, the so-called augmented matrix would be found by copy-pasting your coefficient matrix A and then drawing in a vertical bar and then just attaching the vector B to the right side of that coefficient matrix. So this matrix with 4 columns in total would be what we call the augmented matrix for this system. The coefficient matrix that has been augmented by attaching the vector b on the far right side. And typically we do put a little vertical bar in here just to keep track of which part of this matrix came from the coefficients and what part of this matrix came from the outputs of the system on the far right side of the equal sign. So basically the vertical bar is representing these equal signs in the system. Let's talk about how some of the actions that we took in the previous lesson when solving these systems, let's talk about how some of these actions show up in the augmented matrix for the system of equations. So when we're solving a system of equations, one of the actions that we might take while solving the system is just to take the equations in the system and rearrange them, like shuffle them around. So for example, if I'm solving a system that has a 2x plus 3y equals 4, and it has 4x minus 5y equals 1, it's not going to hurt me at all if I took those two equations and just swapped their order in the system. If I write the second equation first, 4x minus 5y equals 1, and if I write the first equation second, 2x plus 3y equals 4, if I just shuffle those equations around, it's not going to make any meaningful difference in terms of the solution set. So something like this is not going to have a real effect on the solutions that I get to the system. So the corresponding action on the augmented matrix slash the corresponding action on the coefficient matrix would just be to rearrange the rows of that matrix and to shuffle those around. So if I go ahead with the coefficient matrix for this system, the coefficient matrix would be 2, 3, 4, minus 5. And for the shuffled version, the coefficient matrix would just be 4 minus 5 in the top row and 2, 3 in the bottom row. So here I've just swapped the rows. Similarly, if I consider the corresponding effect on the augmented matrix, the augmented matrix for this system would just be the coefficient matrix and then a vertical bar and then the outputs 4 and 1 on the right side attached as an additional column. And this action of swapping the two equations would manifest as swapping the two rows in the augmented matrix. One of the other actions that we have taken as we're solving a system of equations by elimination, one of the actions that we took quite often was taking one of the equations in the system and multiplying that equation by a number, scaling the equation to create a pair of opposite terms that'll cancel out. So if I performed a similar action on the corresponding coefficient matrix for the system, or on the corresponding augmented matrix for the system, that would correspond to scaling one of the rows. Let me show you that. So if I had a system of equations like x plus 2y equals 5 and negative 3x plus 9y equals 2, then an action that I might reasonably take is to multiply the first equation by 3 to create a pair of opposite terms in the x's position. So if I was working instead with the coefficient matrix for the system, the coefficient matrix for the original system would be the coefficient 1 on x, 2 on y, negative 3 on this x, and 9 on this bottom y. And the corresponding action on the coefficient matrix would be to scale that first row. Every entry in the first row is getting multiplied by this 3. Similarly, the equivalent action on the augmented matrix for this system is the augmented matrix would be 1, 2, bar 5, minus 3, 9, bar 2. And the corresponding action on the augmented matrix would be again to scale this top row. So 3, 6, 15, negative 3, 9, and 2. So this would scale the first row of the augmented matrix. That would be the equivalent action in terms of the matrix representation for this system. The third action that we have taken as we've been solving these systems of equations is to add two of the equations together, to add the first equation into the second equation. So the corresponding action in terms of the matrix that we're using to represent this system is to add one row into another row. And let me show you what I mean by that. So for example, if I had the system where it was x plus y equals 0, and x minus y equals 2, then the action I might reasonably take is to add these two equations together to cancel out the y's in the system. And so that would leave me with, if I add the first equation down into the second, that would turn this second equation into 2x, the y's would cancel, and then I would get 0 plus 2 in the back. If I consider the corresponding action on the coefficient matrix for this system, the coefficient matrix originally was 1, 1, the coefficient of x and y, as well as 1 minus 1, the coefficient matrix of this x and this y. And after adding the first equation into the second equation, we get 1, 1, 2, 0. And so this is just add row 1 into row 2. Similarly, the corresponding effect of this addition on the augmented matrix the original augmented matrix would be 1, 1 bar 0 and 1 minus 1 bar 2. And the corresponding effect would be again to add the first row into the second row. 1, 1, 0, 2, 0, and 2. Add row 1 into row 2. So these are the three main actions that we take or that we might take as we are solving a system of equations. And these are the three corresponding actions on the matrices that represent the system. There's the action of swapping rows and changing the order of the rows in the system. There's the action of scaling a row. And then there's the action of taking one row and adding it into another row. And these three actions that we are performing on the matrices that represent a system, these three actions are called elementary row operations. The three elementary row operations are number 1, swapping rows, number 2, scaling rows, and number 3, adding one row into another row. So now let's go through the full process. Let's go back to the system of equations that we solved yesterday by elimination. And at each step of the process, let us track what would be the equivalent elementary row operation as performed on the system's augmented matrix. So in the previous lesson, the first thing that we did was multiply the second equation by 2. So that left my first equation in the system alone. And that turned my second equation into 2x plus 2y equals 4. Now, meanwhile, the augmented matrix for this system is the matrix 2, 3, bar 1, negative 1, 1, bar 2. And if I think about the corresponding action as being performed on this augmented matrix, the corresponding action would be to scale the second row by 2. So that would turn my augmented matrix into 2, 3, bar 1, minus 2, 2, bar 4. So that would be the augmented matrix at this stage in the solving process. Now, solving this system of equations, the next thing that I would do is I would add these two equations together. I would add them together with the hope of eliminating x from this system. So I would add equation 1 to equation 2. And if I do that and I add 2x into negative 2x, that eliminates 2x from that position in the system. If I add 3y to 2y down here at the bottom, that turns it into a 5y in that position. And if I add 1 to 4, that gives me a 5 on the right-hand side of the equal sign. So that would be our location at this moment in the system solving process. Meanwhile, in the augmented matrix, here the corresponding action would be to add row 1 to row number 2. And so if I add row 1 into row number 2, then that changes the second row of the augmented matrix into 0 from adding 2 into minus 2, 5 from adding 3 into 2, and 5 from adding 1 into 4. And so finally, we're at a point where you could relatively easily solve this second equation in the system for y, right? Specifically, to solve this second equation in the system for y, we would go ahead and divide equation 2 by 5. And that would turn this second equation into a somewhat clearer statement about y, which is that y is equal to 1. The corresponding action on the augmented matrix is to divide row 2 by 5. So after that, we would just end up doing then back substitution to find x. So the reason that I had us go through this process, right, is because every single action that we have taken when solving a system of equations by elimination has an equivalent action in terms of just processing and manipulating the system's augmented matrix. And from a computing point of view, solving the system by following this process and manipulating the augmented matrix is much, much more efficient. This is a much better and more convenient data structure for this problem because the computer can very easily hold just this table of numbers that represents the system. And once again, because matrix and vector calculations are very efficient in most modern computers, these actions of scaling rows and adding rows together, once again, can be done very, very efficiently from a computing point of view. So especially if you're solving systems by computers, it's much easier and faster to solve them by manipulating the augmented matrix using these steps than it is by manipulating the system of equations using these steps. So that's why we're going to be moving in this direction. This is faster and more efficient, especially from a computing point of view. Let's go through this quickly for the other two systems that we looked at yesterday. And you may recall that this is the system that ended up having no solutions. So let's see what that looks like in the augmented matrix for this system that had no solutions. So I'll go through it relatively quickly just to avoid wasting too much of your time. The action that I would perform in the system to solve this equation would be to multiply the second guy by 2. So if I scale that second guy by 2, I end up with the equation negative 2x plus 2y equals 4. And then I would add the second equation down into the first equation. And that would eliminate both the x's and the y's. And so that would give me the equation 0 equals 4 as a result of doing that. Now let me track those same actions as they manifest in the augmented matrix. If I represent this system just using a nice clean table of values, the action of scaling the second equation would become the action of scaling the second row. And if I then add one row, the first row into the second row, then that's going to turn my augmented matrix into 2 minus 2, 0 in the top position and 0, 0, 4 in the second position. So left side of the bar, we have all zeros. Right side of the bar, we have a non-zero number. And so this is the augmented matrix equivalent of what we got in the system, 0 equals 4. Finally, let's return to this system of equations that we had that was underdetermined. And let's see how that underdetermined system shows up in the augmented matrix. So for this underdetermined system, again, our process was to scale the second equation and then add together. And when we did that, we got a statement that was completely trivial and vacuous, 0 equals 0, which is always true no matter what. Now, if we look at the corresponding situation in terms of the augmented matrix for the system, 2 minus 2 bar minus 4, negative 1, 1 bar 2, scaling the second row by 2 gives us minus 2, positive 2, and 4. So if we add row 1 down into row 2, we end up in the augmented matrix with an entire line of zeros in that augmented matrix. And that's the augmented matrix equivalent of having 0 equals 0 in this bottom position in the system here. So just bear that in mind. We will be exploring this particular pattern in the next several videos, but bear this in mind. If we had a system of equations that had one solution, in our bottom row, we ended up with a non-zero value to the left of the bar. Notice that in the case where we had no solutions and our system was inconsistent, we ended up in a situation where we had zeros to the left of the bar, but we had a non-zero value to the right of the bar. And that was the matrix equivalent of having 0 equals 4 coming out of our system. And notice in this case where we had an underdetermined system that had a free variable, that manifests in the augmented matrix as this row in the bottom that has zeros in every single position, zeros to the left of the bar and zeros to the right of the bar. This is the augmented matrix equivalent of having 0 equals 0 in your system. So that concludes today's lesson, kind of part one or step one of learning how to represent and solve systems using a matrix representation. A system of equations is equivalent to a matrix equation. If you build a matrix A from the coefficients in the system, if you build a vector x from the variables in the system, and if you build a vector b from the values on the right-hand side of the system, then your system of equations is exactly the same in its meaning as this vector equation ax equals b. These are exactly the same thing, they're just formatted and expressed in different ways. Now, representing a system using a matrix is really convenient because matrices containing numbers are super efficient data structures from a computing point of view and much more efficient in terms of storage of information than the full system is. So if we can represent a system just using a table of values, that's going to be great for us in terms of efficiency. Now, when we're dealing with systems of equations, there are two main matrices that are used in practice. The first one is just the coefficient matrix itself, and the second one is what we call the augmented matrix. The augmented matrix is the coefficient matrix with an extra column, where we just take this output vector b and attach it to the coefficient matrix on the right. And if we have our system that's being represented using an augmented matrix like this one, all of the actions that we perform on the system have a corresponding action on the augmented matrix. For example, swapping the equations corresponds to swapping the rows, scaling the equations corresponds to scaling the rows, and adding the equations together corresponds to adding the rows together. And so every single action that we take as we solve a system of equations has a corresponding action that we perform on the augmented matrix. And going forward, what we're going to do is basically create the augmented matrix, leave the system of equations behind, and perform the elementary row operations on the augmented matrix only. Because this, particularly from a computing point of view, performing the actions on the augmented matrix is much faster and is much more efficient than trying to perform those actions on the actual system of equations with all the variables still in it.